big part of understanding, a big part of working with any science is trying to make connections and trying to make understandings of situations that are new to us. A couple methods that we'll use in this course quite a bit are modeling and the scientific method. Modeling is exactly what it sounds like. Modeling is creating a model or an analogy so that we can compare an unfamiliar concept with a familiar concept. We'll do this a lot in this class in order to help us understand unfamiliar concepts. Modeling is not 100% accurate by any stretch of the imagination. For example, comparing light waves to water waves, they are distinctly different types of waves, obviously. However, we're familiar with water waves, and we can visualize water waves. We're not familiar with light waves. We can't really visualize light waves right now. So by making that model, or that comparison, or that analogy, it helps us to further our understanding. And scientists do this routinely in all branches of science, not just physics. And it's a way of expanding our understanding of more complicated concepts. And we will do that quite a bit. Another method that we will use quite a bit in this course, and actually demonstrate quite a bit in this course, is the scientific method. And the scientific method is a standard problem-solving procedure that you have probably used many times already in your life without even knowing it. For example, if you're driving along in your car and you have a rattle in the car door, what do? Well, the first thing you actually do, whether you realize it or not, is observe. You take a look. You listen. You say, where's that rattle coming from? Is it from inside? Is it from outside? Is it from the window, from the door handle? And that's the same thing a scientist does. A scientist observes. If you want to talk about Isaac Newton with his quote-unquote discovery of gravity, what did he notice? He noticed, hey, this object always falls straight down at the same rate as this other object. So then you come up with, after your observation period, obviously, which in science can last a long, long time. With your door handle, or with your rattle in your car door, it's going to probably be a little shorter time. But after your observation period, you're going to come up with a hypothesis. And a hypothesis is an educated guess. It is not a wild guess. It is an educated guess as to why something is happening. It's based upon evidence, observations. And then, of course, what you do with your hypothesis is you test your hypothesis. And in testing your hypothesis, that's the experimentation phase, you either confirm your hypothesis or you dismiss it. And quite often, most often, your hypothesis tends to get dismissed, and you have to come up with a new hypothesis in science. And this could happen in the real world as well. Where's your rattle coming from in your door? You think it's from the handle. The handle's loose. You examine the handle, it's not loose. So you have to go back and come up with a new hypothesis. If you have enough documentation to support your hypothesis, then you publish it as a theory. Here's what happens. Here's what I think happens. Here's why. Here's what it's based upon. Once you publish your theory, then everyone else in the scientific community wants to take a look at it. And they do experimentation on it. They, of course, want to do one of two things. They want to shoot down your theory, which kind of puts their name in the paper, or if they can't shoot down your theory, then they confirm your theory. And if enough people confirm your theory, then we end up with what is called a scientific law, such as our quote-unquote law of gravity. Now, scientific law is not like a societal law. Society laws are restrictive. Don't run this stop sign, don't go over this speed limit, don't steal, etc., etc. These are restrictive laws. Scientific laws are not restrictive, they're descriptive. Scientific laws try and describe what happens in nature. And once it is a law, it is not set in stone. Laws are still open to experimentation and interpretation. For example, one of our laws that's widely considered by people to be ironclad within the scientific community, we know better, the law of gravity, which says that all objects accelerate towards the Earth at the same rate. There are actually some scientists out in Colorado using an abandoned mine shaft that are dropping objects down a mile-long mine shaft that has been evacuated of almost all of the air. And what they're finding is that there are some objects that actually fall just a little faster than other objects. Now, to the average person, this is no big deal, but in the scientific community, this discovery of a kind of anti-gravity force would be unbelievable. The bottom line is that laws are not set in stone. They are always open to interpretation, and we'll come back to that concept. But getting back to what physics is. Once again, what is physics? You should know the definition of physics. Again, it is the study of matter and energy and how it transforms from one form to the other. And if we're going to talk about the study of matter and energy, then we need to define these terms, matter and energy. Let's start with energy. What exactly is energy? Well, energy by definition is the ability to do work. And this is a concept that we are going to spend considerable time on in this course. So for right now, we will simply touch upon it. The concept of work in physics is, again, a concept that we will spend considerable time on. Work is the expenditure of energy. Energy is the ability to do work. So they are obviously very much related terms. But what exactly constitutes energy in our known universe and the ability to do work? Well, quite honestly, pretty much everything has the ability to do work in one way or the other. And again, in its broadest sense, this is true. So saying physics is the study of matter and energy is kind of like saying sociology is the study of people. You have to categorize that, all right? And that's what we're going to do. So when we say, for example, energy is the ability to do work, what do we mean exactly from here on in when we use the word energy? Well, when we use the word energy, we're going to more or less be talking about pure sources of energy, sound, light, and heat. These are substances, concepts, whatever, that are not considered to be matter. If it's not matter, it's energy. If it's not energy, it's matter. So what is matter? Matter, and you probably kind of already instinctively know this, matter is described by physical properties. And you can describe it by those physical properties. And we're going to take a look at some of those physical properties in just a minute. So let's talk for a minute about pure energy and energy in general, the capacity to do work. What exactly, again, a very broad term, energy, the capacity to do work. Well, we're going to subcategorize this as well. In terms of energy, just like in terms of people, there are all kinds of subcategories we can go down to. But with energy, we're going to go to two broad ones, starting with potential energy. And you probably already know this term from years ago, your study of physical science in grade school. Potential energy is stored up energy. It's the potential to do work. And potential energy can come from a variety of sources. Certainly there's gravity. You know, if I drop a bowling ball out the window, it's going to impact the ground. Work is going to be done to the ground. Why? Because of gravity. Gravity is going to accelerate the bowling ball and it's going to hit the ground with a certain amount of force, and we'll look at that later on. If I use a rubber band to shoot an object across the room, or to attach to a little wind-up airplane toy, again, that stretching of the rubber band, or for example a bowstring, is a source of potential energy, and that's elastic potential energy. Certainly chemical reactions, you learned last year, can produce a lot of heat, a lot of light. There's a lot of chemical potential energy. The gas in your gas tank in your car is a perfect example of chemical potential energy. That gasoline gets burned and exploded and makes your car move in an elaborate system throughout the engine, but ultimately that gasoline is a chemical reaction that causes your car to move. So that's a form of potential energy. There are, of course, other forms, nuclear, there's a lot of other forms of potential energy, and once again, we will come back to these terms. These are terms that you need to be aware of because we will come back to them and use them quite often. Now, if energy is not categorized as potential energy, then it's energy that's being used, which is what we call kinetic energy. And kinetic, again, is a word that means moving, and that's exactly what kinetic energy is. Kinetic energy is the energy contained by any object that's in motion. And notice motion is in quotes here, because we'll come back to that. What's motion? Motion is defined in terms of a very specific set of rules as well. And when we study our kinematics, our study of motion, we'll come back to that definition. But if we do consider an object to be moving, then it does have kinetic energy. For now, we need some kind of defaults. So what do we consider to be moving? Well, for now, we consider the surface of the Earth to be stationary. We do truly understand that the Earth is rotating, it's going around the sun, it's part of a galaxy, etc. But ultimately, for our purposes, we're going to consider the surface of the Earth as standing still, and anything moving relative to that is moving. And again, we will come back to this concept right here. So this is a very broad definition of energy, but it's a very accurate definition of energy. And it's one that we need to know and one that we will come back to. Energy is the capacity to do work, and it can be subcategorized. Now, if we are not talking about energy, then what are we talking about in physics? Well, we already said we'll be talking about matter. And what is matter? Matter, essentially, if it's not energy, it must be matter because it has certain properties. Properties meaning things we can measure, things we can quote-unquote look at. For example, mass. Mass is a term we have used quite a bit already, used it certainly a lot last year in chemistry. What exactly is mass? Mass, by definition, is how much stuff you have. That's it sounds kind of rough and loose, but that's a perfect definition for mass. It's the quantity of matter that you have. It's essentially how many protons, neutrons, and electrons do you have altogether. 3 grams, 3 kilograms, etc. So again, mass is a matter of how much stuff you actually have. And again, something that has mass is not pure energy. It's matter. In addition to mass, it also has inertia. Inertia is a concept that is a little more difficult to visualize, but inertia is anything that has mass has inertia, which is a resistance to a change in motion. And the more mass you have, the more inertia you have. And that makes kind of intuitive sense to us. What's harder to stop? A locomotive going at 10 miles an hour or a small compact car going at 10 miles an hour? Well, of course, the locomotive is harder to stop. Why? It's bigger, it has more mass, and as a result, it has more inertia. Inertia is something that we can actually kind of see as well. For example, if you have a shallow pan of water and you're walking through the yard with it, and why you'd be doing this, I don't know, but if you did, and you sharply turned, the water would quote-unquote spill out of the pan. What happens there, of course, is when you sharply turn, the water's inertia resists that turn. And that's what makes it spill out of the pan. If you have some, fuzzy dice or something hanging from your rearview mirror of your car, and you accelerate, the dice seem to swing backwards. They don't really swing backwards. They're standing still, and they want to stay standing still. So when you accelerate the car, they stay standing still. And so to you, they appear to swing backwards. That's the inertia of the dice. And of course, the string acts on them and pulls them along. And we will talk about that too. These are not the only properties of matter, but they're the key properties. It's matter if it has mass and inertia. What other properties of matter are there? Well, there's a lot of other properties of matter. And again, many that you're already familiar with. Volume. Volume, again, is how much space the matter takes up. Volume should not be confused with density. Mass density is the ratio of the mass to the volume. The old trick saying, what weighs more, a pound of lead or a pound of feathers? Well, they weigh the same. They have the same mass. However, the pound of feathers is going to take up much, much more space. So the pound of feathers has a greater volume, even though they have the same mass. So mass density is the ratio of mass to volume. And again, intuitive sense to us. If you have a substance like, for example, lead, where the molecules are really packed together tightly, all right, then you have a lot of mass in a relatively small space. That's a relatively high density. So it's the ratio of mass to volume. By ratio, again, we mean a fraction. So what we're talking about here is a relationship that can be described by a mathematical equation. And you can see this red box that we put around our base equations in this course. This is an equation, but we really want to think about it as a relationship. What this formula in the red box says is density is directly related to mass, yet inversely related to volume. And we will spend a lot of time understanding relationships among variables in these concepts. So again, density directly related to mass. What does that mean? As one goes up, the other goes up. The more massive, the more dense if they're the same volume. Inversely related to volume. What does that mean? Inversely means as one goes up, the other goes down. So if we're talking about the same mass, keeping the mass the same, if we have a greater volume, we must have a lesser density. So density equals mass divided by volume. That gives us units, of course, to deal with of grams per cubic centimeter. Most of the densities we're going to be talking about, this is the basic unit for density, but we can also be talking about kilograms per liter and many other units, and we will get into a discussion of units later on. For now, these will be our standard units for density, grams per cubic centimeter. Now, that equation, density equals mass divided by volume, once again, that is one single concept, one single relationship. Density is directly related to mass, inversely related to volume. All right, this again is one single concept, but obviously mathematically we see it as an equation in three variables, which to us means that it's three equations, and we will use it in all three ways. But the concept doesn't change. For example, if we manipulate this equation algebraically for mass, we get mass equals density times volume. This is still the same relationship. Density is directly related to mass, yet inversely related to volume. Of course, the units here for mass would be grams, because the density units, grams per cubic centimeter, the volume units, cubic centimeter, would produce that. Of course, there's one more way to look at this equation. Volume would equal mass divided by density. Once again, a third equation, but still one concept. This equation still says that density is directly related to mass, yet inversely related to volume. This is the concept we really want to learn and hang on to. The equations will take care of themselves if we learn the concepts. And that's going to be the key to being very successful in this class. So again, as we see this equation here, we understand it is inherently three equations because it is three variables. And for our purposes, these are all really the same equation because it's the same concept. And we can use any one of them as we need them in our problem solving. Now let's spend a minute to talk about how we properly solve problems. And again, this concept of mass density is not new to you. You've done it many times before in your science career. But let's talk specifically about how to properly solve problems because of the fact that we will be doing quite a bit of that in this course, much more so than you've done in your previous science courses of biology or chemistry. Now, when we solve problems in physics, we follow a set procedure, and step number one seems very obvious, but it's very often a neglected step. We must read through the entire problem before we go to solve the problem. It seems like a common sense kind of thing, but many students neglect to do this, and what they do instead is they read till they hit a number and then start writing down numbers, and they lose the continuity of the problem, and in more complicated problems they solve for the wrong thing. Again, we want to avoid mistakes, so we will read through the entire problem. Once we do that, we will always list the given information. What do we have? What do we need? You know, our quantity with our numbers, with our units. We always want to have that listed, because if we don't know what we have and we don't know what we need, we cannot go any further. Once we've decided what we have and what we need, then we're going to go and find our base equation to come up with this information. Now, right now we have one single equation for density. Down the road we'll have many kinematics and dynamics equations and different equations to use to solve for unknown information. So we have to make sure that we choose the right base equation, and again the equation comes from understanding the concepts and the basic content. Then we're going to put our numbers in and we'll solve it on our calculator. We're not going to do calculations on paper. We're not going to show our division or any of that kind of stuff. That's what we have calculators for. And then what's important also as part of this course is that we're going to circle our final answer with, of course, correct units. A final answer that needs units must have units. If we're talking about mass, you can't simply answer 15. What does that mean? 15 grams, 15 kilograms, these are decidedly different values. So you must put your units in there. And then the reason we circle our final answer is because down the road we're going to do some very complicated problems with multiple steps involved, and we can't simply have answers laying all over the place. Ultimately we'll be looking for one final answer, and you need to show that. Let's take an example and take a look at an example of how to employ this problem-solving procedure. Again, a procedure that you've already learned throughout your career here in math and science at Mount Carmel, but one that we're going to put particular emphasis on in this course. Here's our example density problem. Very simple problem that you probably could have solved in 6th grade, but this is how we like to start out. We start out simple, get our feet underneath us, and believe me, we'll challenge you down the road. First thing we want to do, of course, read through the problem. What is the density of a rectangular object that has a mass of 63.2 grams and is 3.42 centimeters long, 1.09 centimeters wide, and 2.56 centimeters in height? Now our second step in proper problem-solving technique is to list all the given information. And the given information means what do we have and what do we need. I encourage you to go through the problem and list the given information as it's given to you in the problem. Many students will look at this problem and say the first given piece of information is that it has a mass of 63.2 grams. But that's not correct. The first given piece of information in this problem is actually what is the density. The most important piece of information you have in the problem is what you're looking for. And in this problem, that's the very first thing you're given, what you're looking for, density. Then we're told it's a rectangular object. That's nothing that we write down, but that's important for us to know, because if it's a rectangular object, we know that density, of course, is going to be found by taking length times width times height, as opposed to if it was a spherical object. But in this case, again, it's a rectangular object with a mass of 63.2 grams. And notice how we write that down. We have the quantity, represented by the symbol M, and then the number, and then the unit, represented by the symbol G. And then, of course, we have that is 3.42 centimeters long, and later on we'll just call everything a length. But for right now, we'll be a little more descriptive. We have a length, we have a width of 1.09 centimeters, and we have a height of 2.56 centimeters. Now again, this is a very simple problem that I'm sure all of you could do with no difficulty at all. But again, we are trying to develop good work habits here. So what is our next step in our problem-solving technique? Get our base equation. And our base equation here is going to be density is directly related to mass and inversely related to volume. D equals M over V. Again, trying to understand the concept and not just the variables. Now we can't solve this problem right now because do we have the mass? Sure. Do we have the volume? A lot of guys will say, sure we do. But we don't have the volume listed as any part of our given information. But of course we have the length, the width, and the height, which will give us the volume. So we need to show that. Volume equals length times width times height. Or we can just substitute it right into our base equation. Density is going to be mass divided by length, divided by width, divided by height. Now we put our numbers in the right place in the equation. And we don't have to show any more work than that. Now when we do this on our calculator, again, make sure that you punch the numbers out correctly. 63.2 divided by 3.42 divided by 1.09 divided by 2.56. And that will give us, if we do it correctly, 6.62 grams per cubic centimeter. Last step of our problem solving procedure is to circle that final answer. All right, and again, we want to circle that final answer to make it stand out, and when we have more difficult problems down the road with many steps down the road, we will need that final answer to be set apart from many of the other calculations within the problem. Now, as part of this slideshow posted on my website, which is mchs.org/coache, which you can again find under the For Students tab on our website, you can download this slideshow presentation, and as part of the slideshow presentation, you will see 6 problems that you need to solve. Okay, these problems need to be done showing all of the work in proper problem-solving technique. So you must demonstrate that you understand how to solve problems correctly. Label those problems, okay, and then properly solve them. And you can solve them in a Word document and then attach that work and send that to me at physics@mchs.org, following the procedures that are posted on the website for your summer assignment. If you have any questions, you can also, of course, email me. And again, I hope you have no difficulty with this material. It should not be much of a challenge for you, but it's very important material that you be able to bring to class with you on the first day of class. You will be expected to already know this material on the first day of class. Thank you, and I look forward to seeing all you guys in class in the fall.